My name is Ajay Kulkarni. I'm the co-founder CEO of a company called Timescale. We're a new company building an open source time series database that combines the query power and ease of use of a relational database with the scalability of NoSQL. And we're based in New York. But let's actually talk about time series data, which I'm assuming why you guys are here. And time series data has actually been, I think, quite trendy lately. It's been, I think in several talks at this conference. How many of you were at the time series database panel? Saw that on the first day? Yeah, cool, great, yeah. And so the question is why? Like, why is it so trending? And or why are we talking about it? Because it seems to be the fastest growing database category in the past 24 months. And so the question, then comes is, what exactly is, time series data? And even some of those, I see some people in the room who are working in a time series database. Even if you think you know what a time series data is, I would argue it's actually, I think, more than what you think it is. The next question is, okay, from that time series data, why do I need a time series database? And sometimes you may not. Sometimes a normal database may be fine, but I'll talk about why, in most cases with time series data, why you need a time series database. And finish off with is this just a fad or is this going to continue? And we don't think it's a fad. Before I go forward, who here currently has time series data? Great, 3-4 people. Who here is working on a time series database? Yeah, that's cool. Yeah, neat. Yeah, well, good.
Does graphite count?
I think it counts. I also think Prometheus counts, but I think it depends on who you ask. Let's go through some examples of, first, what is time series data? And I'd be curious to hear, of what category your data falls in. When most people think about time series data, they typically think about, DevOps metrics and logging, right? They think about, tracking CPU, memory usage, alerts, status. In fact, the panel on Tuesday, if you think about the people who were on the panel, it was, Prometheus, Elastic, Influx, ClickHouse, Beringe by Facebook, and Timescale and us. And most of them were primarily focused on the DevOps use case. So I think this is what most people think of. So, okay, that's time series data. We come from New York City, and New York obviously has a lot of the finance industry. And in fact, finance industry has a lot of time series data. They have, stock records, payment records, transaction records, and in fact, a lot of the first time series databases were designed for financial use cases. So it's okay, that's time series data. There's event data. Prior to Timescale, I spent the previous 10 years in the mobile industry, running the mobile engineering team at a group messaging app called GroupMe. It's actually a screenshot from GroupMe, and we had a lot of event data that was clickstream data, application events. Errors, and I would call that time series data. There's also IoT data. Everyone talks about IoT. In IoT, you have sensor data, machine data, industrial monitoring, the smart home, wearables, and in fact, the company that is now Timescale, we actually started off as a slightly different company focused on IoT as an IoT platform, and we needed a place to store all our sensor data that we were collecting, and so we ended up building Timescale initially for our own platform, and then the database kind of took a life of its own. So we kind of pivoted the company to that. But we feel this pain because we need a place to store all our IoT time series data. So I'd call that time series data as well. And there's also other data, like data that you wouldn't normally think of time series at all. There's one company that we work with is in the logistics business, and they track assets. There's a shipping company, they track assets all over the world. And in the beginning, when the company was first founded 100 years ago, they were tracking assets on pencil and paper, or maybe ink and paper. And then in the past 20 years, they moved towards barcode scanning, right? And so first you had time series data and paper, then barcodes, and now they're in the process of deploying sensors to actually collect automatically time series data. And they're someone that's not they're not in in a super tech industry, but they also have time series data. So that's 5 different categories, 6 different categories, and the question is which of these is time series data? We'd say it's all of the above. so kind of coming back to our initial question is, what is time series data? What's the common thread across all these applications? And we think it's actually three characteristics that we believe define time series data and time series workloads. The first characteristic is, obviously it's time. Time is an important dimension along which you are capturing and analyzing your measurements and events. Number two, the workloads tend to be primarily inserts. You're generally collecting data and just writing new data points. Every now and then you may update a previous data point because of an incorrect measurement, but you're rarely making updates. It's really primarily inserts. And number three, most of these inserts are to the most recent interval. You're not randomly inserting across a database. You're generally inserting across in time. You may have some delayed data, but it's generally to the most recent time series. Generally when we think of this combination, it's generally called append only. So like to say time series data workloads are append only. Would this resonate with maybe what you have? Yeah, sure, cool, yeah. Feel free to jump in with any questions, by the way. Well, then, the question you might ask is, okay, well, how is this different than just having a time field in your data? Like, I have a time field. Is that time series data? And we say, well, it depends, right? It depends on, how do you treat changes, right? Time series data, they treat changes in the system as inserts, right? Traditional database workloads, traditional relational database workloads, OLTP workloads, treat changes as updates. Right, so I think that's the primary difference is that as changes come in, we're just recording the delta. Not the delta. We're recording the new change. And in fact, I would say you may have time series data and not realize it. We were talking to a company earlier at this conference. In the container business, not in the Docker business, but the actual physical container business, and they track the goods that are shipping in their containers, right? And the way that you traditionally track this is they would say, okay, container ID foo currently stores this blob of shipment, and when that blob gets moved out, another one comes in, they update the entry for foo and say, here's the new blob, and then they realized over time that they had to ask the kind of questions that they couldn't answer. They had to ask, well, a month ago, a customer's complained that a month ago we didn't ship the right thing. What was this container holding a month ago? And by updating that record, they actually lost it, right? And so now they're actually thinking like maybe we should treat those changes not as updates but as inserts and actually treat the actual contents of each container as a time series data. And so, that kind of hints at my next slide, which is, why should you be thinking about maybe shifting towards either having time series data or shifting towards from an old mind frame towards a time series mind frame? And it's a few reasons. Number one, like the example I just mentioned, with the past, you can analyze historical trends over time, but you can also say at any given point in time, look at the state of the system at that point in time. A month ago, what was the state of all my containers across all my geography? In the present, having time series data granularity lets you monitor your system in real time, but also troubleshoot errors as they occur. And then obviously in the future, this is kind of where I think everyone wants to be, is with time series data granularity, you can actually identify and fix problems, identify future problems and fix them before they occur, reducing downtime. Any questions so far? Yes?
So we have a chat system.
Okay.
And we keep track of changes as they get changed.
Yep.
We do overwrite things.
Yep.
So we have a locality that we know the history is stored with,
Yep.
Whatever the changes are. And if we just do an append-only thing, then trying to aggregate it, trying to figure out, what the changes are, we have to wait until all this data.
Yep.
Changes apply. So I assume you're going to address them.
Yeah, well, I can address that now. I think I'll talk a little bit later. I'm not saying right now that you necessarily should move everything towards a time series workload. Sometimes you may want to have, I think mainly for performance reasons, having like a kind of a cached view, I think, of the state of the world instead of at any given point computing everything. But then I would say, maybe you actually keep the time series granularity and then use that as a view on that data as opposed to separate data. Does that?
Yeah, that sounds fine.
Yeah, cool. Okay, so that's time series data, but what does it look like, right? And we think it actually doesn't look like what you might think it looks like. So this is what we've been told. We've been told that a time series generally has a name, right? Like CPU, the thing you're measuring, and it has a set of tags associated with that name, and then has a stream of essentially time measurement pairs, right? And then when you start recording something new, that's another time series, and now you have free memory, maybe the same set of tags, and another set of time measurement pairs essentially. And look, you may be collecting this data at the same time, but traditionally people have thought of, okay, these are two different time series. But are they? Are these really two different time series? And we actually think that's a wrong way of looking at the world. We actually think that time series data actually has a much richer structure. We found that most of the time, not always, most of the time, you're collecting multiple measurements at the same time. And your data has this inherent structure that if you have it, you shouldn't force it, but if you have the structure, you should preserve that structure. Because based on that structure, you can actually ask questions you couldn't do before. And even looking at this, this to me, coming from like the relational database world, feels like a more intuitive way of looking at the data. You have, for each time, you have a row of measurement values. And then when you start looking at it this way, you can ask new questions that you couldn't before. You could ask, first of all, you run fewer queries. So while before, this would have been 3 different time series, you would have to, run a select query 3 times. Now you're just running once, right? Okay, fine. It's one kind of a minor optimization. But you also apply complex filters. You could say, okay, like what was the state of the world when the temperature spiked, right? Like what was the corresponding CPU and memory data? You could say, okay, let's actually aggregate memory by CPU buckets, right? And you kind of do complex aggregates. You could say, how does temperature, for example, correlate with memory? And obviously, in this example, there's a correlation. And in fact, you can take advantage of kind of relationships that exist in your data. For example, tags, you might say, well, every host has a set of tags, and instead of storing that with the series, maybe we store that in a separate table, and we kind of map it at query time using like a host ID, right? Now you might say, okay, fine, but in the old world, let's go back to the old world. In the old world, why couldn't we take these 2 data sets and just join them on time and essentially do the same thing? And there are 2 reasons why that's actually really hard. There are 2 scenarios. One scenario is, maybe if your time series data is too coarse, right? Let's say you're collecting data at seconds, you're storing them seconds, but your measurements come in maybe at milliseconds, then you may end up having multiple measurements for the same time, right? So you get duplicate measurements. On the flip side, you may say, okay, well, I can solve that by storing them at nanoseconds, so I'll have higher granularity of my data. But then you're storing that additional information not because you need it for time, but you need it as like a join key. It's really inefficient use of like a join key in time, which is why we think this complex structure works better. Yes.
What about for high cardinality?
Yes. So it's a good question. High cardinality comes down to your implementation. And I can talk to you more about this later, but generally, it's just kind of a quick tangent because I think it's actually relevant. High cardinality is this problem. So the question for the recording is, what about high cardinality? The high cardinality typically is a problem with time series. When people think of it in this world, they say, okay, these are 2 time series, and people say, well, we could only handle 5 million time series. Cardinality typically comes in when you implement your data store using something like a log structured merge tree, where you're essentially solving the kind of the scale problem, right? Because time series data has a high ingest rate. You're solving the scale problem by using like a new type of index, and that index, typically has, a cardinality problem. So I would argue that the cardinality problem is not a nature of time series, it's a nature of the way you implement it. If, for example, log structure merge tree. The way we do it, which I can talk about afterwards, we actually leverage B trees in Postgres, and we do this thing called adaptive space-time chunking that allow us to actually not have a cardinality problem at all. It's a good question, though. Other questions? Okay, so that's time series data. How should we store it, right? Okay, can't I use a normal database? Like, why do I need a time series database? And the answer is you can. You can actually use a normal, MySQL, Postgres, whatever database for your time series data. This is a survey that Percona ran earlier this year with, I think, about 1,100 respondents, and about 40% of respondents were using a vanilla, non-time series database for their data. It was MySQL, Postgres, Oracle. On the relational side, on the NoSQL side, it was like a Mongo, Cassandra, something else. But you may have noticed that we're in this golden age of time series databases, and they're trending right now. And so the question is, why are they trending? Like, what do time series databases add that normal databases did not? Why do I need a specialized time series database? And the main problem with time series data, which I think Austin was alluding to, is that the data typically it piles up very quickly. When you're collecting data at seconds or multiple times a second, or even 5-minute intervals, you're going to hit a scale problem much faster than you would have in a traditional OLTP workload. And these are kind of two different data points. One is connected cars, right? In a connected car, an average generates 25 gigabytes of data an hour. And then if you look at planes, Boeing's 787s generate half a terabyte per flight. That's quite a bit of data. And in fact, what time series databases do is they end up introducing efficiencies to tackle this problem by constraining the problem to time series data, efficiencies that you don't have in normal databases. And it's because time series data is different than typical OLTP data. The classic OLTP example is, if you think about a bank account, let's say Austin and let's say I'm sending Austin some money because I owe money for a beer, and I send him $10. You debit my account and you credit his account at the same time, and so this means you have to in a single atomic transaction, find my account over here and debit it, find his account, which may be over here, and kind of randomly do these updates. And so what you're doing is you're doing a lot of updates. They're randomly distributed because you don't know who's interacting with whom. And you're doing transactions in multiple primary keys. So this is the traditional world. In the time series world, as we discussed earlier, it's actually quite different. You're primarily inserting data, right? You're primarily inserting them to a recent time interval, and in each data is actually associated with a primary key and the timestamp. And because of these differences, time series databases can introduce efficiencies. The efficiencies we see are typically three kinds. One is on the ingest side, having better write rates. On the query side, being able to have query performance even at scale with fewer resources. And number three is typically if kind of common functions, you might require interpolation, you might require different kinds of bucketing. They kind of add these kind of functions that for ease of use.
I don't see compression on here, so.
Yeah.
Would that be one too?
Well, is it for you?
Well, no, you just said that generates a lot of data to go on the flight, right?
Mm-hmm. Yep.
So you want to share?
Yeah. So compression is an interesting thing. It depends. It might for you, and I'd say it depends for two reasons. Number one is typically with time series data, and not always. Typically, the data gets stale after a certain period of time. So you think about like the DevOps use case. You're monitoring data from 2 months ago, 3 months ago. You may not need that anymore. So it ends up getting you have the data retention policies, so you delete it. So many of these use cases, your time series data set. It grows, but you can actually delete old data. Number two is typically the scale problem. You typically see that typically the bottleneck is not disk storage, but it's memory. And it's memory because of the traditional cardinality problem. If you're inserting a lot of data and you want to do it efficiently, you kind of want to keep a lot of your indexes in memory. And so time series databases have optimizations to not require ballooning memory. But you're right. I think for some cases you may require compression as well. Is that something that you're seeing?
Yeah, I'm just thinking like you're in a Tesla and it's recording all the information about you maybe every 3 months it rotates around.
Yeah, no, it's fair, and I think I would say it depends, and I would say you may want to keep that historical data for data science, perhaps, in which case you may not need it in the database. You may want to store it in flat files or like a distributed file system like HDFS, but it's fair. Other questions? How are we doing on time? All right, cool. Okay, and so this is kind of the third part of my talk, which is, time series databases. Is this just a fad? Is this just like this trendy thing, or is this really here to stay? And we think it's here to stay, and we think it's here to stay for. We kind of see like three major drivers. They're kind of converging to make time series data like a thing now. And number one, it's increasing operational needs. I think we increasingly find ourselves managing more and more complex systems. Within the IT world, obviously you have data centers and clusters and VMs and containers and microservices. Within just applications in general, you may be incorporating. I think Baron gave this talk yesterday where you may be incorporating Stripe for your payments and Twilio for SMS, and now you're relying on multiple systems. And because of all this complexity, you need to manage this complexity. You need higher granularity of data to do real-time monitoring, to do troubleshooting as errors occur, and to do better prediction. So we think that's kind of one big driver. A second driver is business needs. There's this constant hunger, or this constant need to make better data-driven decisions faster, right? And another reason why we're seeing this move towards time series is that it's just a higher granularity of data. You're getting data faster with more detail. It lets you make better decisions. Another reason on the business side is we have more sources of time series data. You have kind of new devices coming online that didn't exist before. You have old devices that were essentially siloed and sitting offline, like motors and cars and planes that are now coming online. And then you also have new systems that you didn't have before. And the third is just general tech trends. As storage gets cheaper, as processors get faster, and as bandwidth becomes more ubiquitous and cheaper and broader, you can essentially store more data, you can process it better, and you can backhaul it faster. And then the other piece on the trend side is better resources. We have cloud computing, right? Which makes it easier to spin up instances and actually analyze data, store data, and we have better data analysis tools. And we think it's this convergence that we feel like, I don't know what the term is, but I feel like we've been living in this era of like quote unquote big data, whatever you want to call it, that we're entering this new world that's going to be at higher volumes, higher velocities, and higher granularity. And we haven't come up with a good name for it. Some people call it huge data, which I think is kind of a little lame. But but if you guys have any ideas, I'm open to it. And I kind of want to just kind of close out with a crazy idea. I was working on these slides late last night with the rest of the team, and we'd come back from the party that they had here, and we had drank a lot of caffeine as well. So we had caffeine and alcohol. We're kind of spitballing ideas, and we were kind of thinking like, is alt data time series data? If you think about it, like as data changes, if you decided to not store the latest state, but instead you stored every change as an individual row, then could you convert everything to time series data? in the bank account example, maybe you have an event that says this transaction occurred, and in order to get the latest view of our bank accounts is just a materialized view of time series data. And in fact, doesn't every database have a write-ahead log, which is essentially a time series data set? So I don't know. It feels a little crazy. I'm not sure if I believe it, but I thought I'd throw it out here and see what you guys think.
I think you run into the same, kind of the next issue I wanted to ask you about, sparse data.
Yep.
Because in the relational sense of things, it's not very efficient to store that.
Yep.
Where, column approach is probably better.
Yeah. No, it's fair. It's fair. I again would say that it's an implementation detail. And even in, what's that? I'm sorry, thank you. So the question is, what about sparse data, right? And if your data is especially sparse, how does that affect this relational data model of time series data? And I answer that question two ways. Number one is your time series database. It doesn't need to be relational. I think I'd say most of the time you have this structure, but sometimes you may just want just like a key value store for fast lookup, or you may want a column store. Either of those would work well for sparse data. But I think it's also an implementation detail where our Timescale is built on top of Postgres as a relational database. Postgres has a JSON, has a unstructured store, which is a JSON store, JSON binary, JSON B store. So I think the real answer is if your data is incredibly sparse, then you can store it in a non-table-like way, but it's still time series data. It's fair.
Are there special data structures that are better for storing time that aren't B-trees or LSMs?
So the question is, are there data structures that are better for storing time than B-trees or LSMs? Probably. The best one, we built this in the past 6 months, and we looked at LSMs. We also looked at obviously other indexes, other just like GIN, just indexes. We also looked at influxes. I think they call it a time structured merge tree, which is a variant of a log structured merge tree. We believe that right now B trees, if you size it the right way, that B trees are actually the ideal store, primarily because as long as you can fit them in memory, but you can fit them in memory if you chunk your data the right way. And the advantage of B trees is that it actually it allows you to support a variety of indexes in a memory performant way.
And the second question, so what kind of query, how does the queries differ for time series? And is there any first-class query support in your language that you use? Do you have a kind of preprocessor or something that generates something for a different kind of query language that makes it easier to query time series?
Yep. The question is, how does the query language differ? And then I think questions like, what is our query language? Yeah, so...
what's the typical queries you're going to get for a time series?
Yeah, I wonder if I should switch to... It might take too long, but... So we think it doesn't differ. So this is where you may get into like a religious debate. And the religious debate is, there's the SQL camp, and then there's the kind of the functional camp. And I would put... in the functional camp, I'd put Prometheus, right? PromQ or PromQL is not SQL-like. It's a new query language. Timescale, the way we've architected our database is it integrates very tightly with Postgres. And in fact, we look like Postgres to the outside world. So we support full SQL. In our mind, SQL is not the ideal query language in general. It's probably not the ideal language for time series data, but it's the best one we have right now. And it's the best one because I haven't seen anything better. And everyone knows SQL. And so I would actually argue that your queries, the structure doesn't really change that much with time series data. The operations you run will be a little different. For example, interpolation is something you'll see often in time series data. Flexible time bucketing, something else to see in time series data. We support that through new functions, right? We don't change SQL to support new functions within SQL. And so I would argue that SQL is actually quite powerful for time series, and it's powerful because everyone knows it, which means that if you have an organization where you want your business analysts to analyze your product people to analyze your time series data without involving an engineer, they probably know SQL and they can run their own queries. But it's also the best because there are a lot of tools today that speak SQL. Like if you're using visualization tools like Tableau or SQLpad, they already speak SQL. So I would say it's SQL. And in fact, in the broader database world, there's this movement where we kind of started off in this relational database SQL camp. In the last 10 years, the pendulum swung all the way over here to NoSQL. And now you're seeing a lot of these NoSQL databases kind of adopting SQL-like languages or SQL shims on top. And the joke today is NoSQL actually stands for not only SQL, like they do SQL and something else. So we think it's SQL. In 20 years, will we find something better? Probably. Maybe the machines will query themselves. I don't know. But we believe it's SQL today. Other questions? But no one poking holes on this, huh? Yeah.
Specifically, I mean, anytime a data point comes into being, that's I guess like the timestamp. It's like birth date.
Right.
So every data point is part of some time series data. Even if there's just one, it's a one data point time series.
Right.
So I would say yeah.
Does anyone disagree? I mean, I honestly don't know if I agree, right? So, I mean, what's the counterexample to this statement? What kind of data is not time series in nature? Yeah.
We use the database for idempotencies.
Mm-hmm.
So you need to check the status, and you have also update your records. You need to make sure that they are same. And so in that case, I don't think it's really a time series data.
Yep.
You can't really just have a stream and then at the end you just consolidate them. You need to check in between whether it's a valid operation or not.
That's fair. So the counterexample is sometimes you need to check if it's a valid operation. It relates to idempotency, maybe transactional support as well. But I wonder if that is just a performance problem? Like you could query that off of time series data, right? On the fly. So is it a performance issue? Are you just saying you need a cache, you need a materialized view that makes it easy to check idempotency?
But you mean you can go back to your time series and check to see if
Right.
yeah, but then as you said, there's performance.
Yeah.
So a lot of times you need real time. You go to a bank, you go to ATM,
Right.
you want to withdraw some cash, and you can't really just can you wait 20 seconds?
That's right.
Tell you?
Yeah. But as computers get faster and and memory gets cheaper, at what point does that latency drop within an acceptable latency?
It depends. So we have millions and millions of data points getting into the system.
Uh-huh.
How do you find out something is relevant and something is not unless you go through all this data?
Yep.
Unless you organize them in a very efficient way that you can go right into the stream,
Mhm.
you can look at things faster.
Yeah. No, it's fair. It's fair. Yep.
I mean, I think there's a lot of cases where, you could claim it's time, that you really don't care what time the data came in. That's so secondary. Like a CAD drawing.
Yeah.
Some elaborate three-dimensional drawing.
Yes.
There's a bunch of data there.
That's right.
I don't care what order it came in. I just want the drawing data. The time is completely irrelevant. So that's you could say, well, someone added this part and then this piece and then this line.
Yeah.
You could redraw the whole diagram from all the steps.
Right.
That's pretty nuts.
Well, so the counterexample is maybe another counterexample, maybe a CAD drawing where you just want the file so you can look at it. But and I like this because it makes sense. It totally makes sense. But then I have the same thought, which is
I would argue if you're looking at a CAD drawing, you need to have an undo and a read.
That's what I was actually going to say. Yeah, what about an undo and a redo? Don't you want the constant state of the CAD drawing and your version control and say, then he edited it and then she edited it and who made that, right? It's yeah. No, I'm with you. I'm not trying to sell this theory. I'm with you. I'm like, does this theory even make sense? Like, yeah.
So I would provide a counterpoint in that, let's say you have like a bunch of like temperatures like you were showing before. Like if you want to find out what the average is or the standard deviation, then that number that you compute, like does that really have any time associated with it, right? Like it doesn't really make sense because those are secondary, pieces of data.
Yeah.
There's a distinction between like raw data and then something else that's computed on top of that is derived data.
Right.
From some original source.
So the counterexample is maybe there's raw data, which may be time series. Maybe there's derived data that's computed on top of it. Yeah.
But you can continue that as well, right? You can say I'm looking at the average in the last month and the average the month before, and in a way, averages are just like your current snapshot.
Right.
So you can extrapolate that and say
Right.
it is or it isn't.
Right. But is this just like a reductionist argument? Is this like an absurd argument that you just right?
It does go to some level of, everything has a history, right?
Yep.
Time moves forward from Big Bang or whatever was there at that time.
Yeah.
In that sense, the whole universe is a time series, right? But I don't know, the only thing I can think of is if you have cases like where, you have a juvenile record and then it's expunged and you're not supposed to know about it anymore.
Yes.
Right? Then you don't want to have a time, so you need to eliminate the time series aspect of it, follow the
Right.
the law and stuff. So, but that's more of a business, I guess.
Yeah.
Or legal
Right.
reason to force one or not force one.
Right.
I don't know.
Yeah.
And that everything has a history.
Yeah, that's fair. I mean, and I wonder if the answer is maybe all raw data is time series, but the data you derive on top and how you use it, may not be. Yeah, but it's interesting. That's essentially, the talk. I think it was a little shorter than the slot. We're at about 35 minutes. Again, we're Timescale. We're a new open source time series database. We're thinking about time series data a little differently, as you may have seen from the talk, mainly because when we needed a time series database for IoT platform, we needed something that was totally different than what people were currently offering. And now, as we're building this out, we're realizing that maybe this is actually something useful to more people, which is why we then open sourced it a month ago. If this is something that you feel like it might be useful to you, feel free to check us out on GitHub. We appreciate any stars. We collect stars. Download it, play with it. It's Apache 2 license, very permissive. Appreciate any feedback. Appreciate pull requests. Any questions?
Well,
Yeah.
So, to me, the bottom line is I'm going to choose a purpose-built database for this type of data.
Yes.
If it performs better,
Yep.
faster, and or if it saves me a lot of space. Like that's one of the big things about RocksDB is it can actually save you a ton of space, and therefore you're buying fewer disks and fewer
Yep.
hundreds of servers. So, do you have any stats on Timescale? Does it do those two things for me? How much faster is it?
Yeah. So let me switch to that, and this is going to become more about Timescale. But I feel like people are asking questions about it, so it seems appropriate. Where are you? Let me just do this to be faster. So I think, I think it's really interesting. I think a lot of people end up talking about, compression and disk and storage, and I actually think that's a proxy because I think it's a proxy for cost. I would say you actually don't care about disk size as long as you can get performance and you can keep the cost low. And let me just jump in. So one downside of this relational database approach, as opposed to a column store, which I forget, maybe Austin mentioned it, is that we don't get the best compression. You just can't, right? I mean, I think every row requires, I forget how many bytes, but certain bytes per row, and even if you have nulls, for sparse data, it's going to take up some space versus a column store or a key value lookup. And if you really need a lot of compression, even at the cost of query power, then I would say maybe you'll use something aside from Timescale. But what I would argue is that what you really care about is performance, but cost. And And one thing with our approach is, since we don't have the cardinality problem, memory is less of a bottleneck, and memory is 20 to 100 times cheaper than disk, that it's actually quite comparable with the metric you actually care about. So that was the compression question. You asked a question about performance. And with performance, here's what we've seen. We've seen that, first, compared to a relational database like Postgres, and I'm sure, MySQL would have a similar behavior. Relational databases typically, they don't scale well as your data set grows, and that's what this is showing, is the insert rate as your data set is growing. And it's actually showing that the average insert rate deteriorating, but also becoming more variable, where when you come all the way down here, you don't know if you're going to get, 100 inserts per second or 15,000 inserts per second. And this is because that as data set grows, the B trees grow too large to fit in memory, and end up swapping parts and subtrees in and out. What we essentially do is, we take your data and partition it across time and space. And the performance gain we've seen as a result is essentially horizontal performance. Even as your data set grows, your insert rate it stays fairly constant. And this is inserting 14,000 rows a second, where each row is 10 metrics. And so you're actually getting 144,000 metrics a second on a Postgres database of 250 million rows. And you may say, okay, like this is just 4 gigabytes of memory. What happens if you throw more memory at the problem? And what you get then is, Postgres, the relational database kind of does fine for a little bit longer, but you still get the same problem. You're still pushing it out. And you end up, essentially with the same thing. One thing I want to point out, since you asked about performance, is, this is on a single batch size. But if you end up maybe having like group batches, maybe you're consuming data off of a message bus, and then you kind of insert all at once. So let's say 10,000 size batches. The relational database kind of drops off even faster. And our approach, you get a little bit more variability, which we're trying to figure out, but it's within a pretty good band. And on average, you're getting 1.3 metrics per second. There are also some advantages it's a 15x improvement over relational database. You also get some, query performance improvements. For most types of queries, we're essentially about the same as a relational database, or a little bit faster. But for some others, we're actually quite faster, and in fact, we're so much faster here that it doesn't even fit on the graph. And so obviously you get advantages as well. One thing we're in the process of doing now is benchmarking approach versus other kind of NoSQL databases and traditional time series databases, which we haven't published yet. Not because we don't like the numbers. It's actually funny. We like the numbers a lot. So we're actually even more hesitant to publish them, because we're like, are we missing something? And we want to be particularly fair with our benchmarks. We don't want, we hate when people cherry pick benchmarks. And so we're in the process now of kind of running kind of thorough benchmarks. We want to show where we do well, where we don't do well. But we're actually finding we do pretty well with most query patterns. But we should have that in the next month or so. Other questions? I did not expect to get into this, but I'm glad we're asking these questions. Other questions on Timescale, time series data? Okay, I'm going to do a quick poll before we leave. Maybe just go around the room really quickly. What kind of time? I'm just really curious. What kind of time series data do you have? And if you don't have any, you can just pass.
Well, advertising.
Yep.
But we do not keep all the data. We keep like for the last in production couple months. We keep dropping all the data.
Okay.
Backups.
And what are you using today?
MySQL.
MySQL. That's great. Yeah. Anyone else?
A lot of system metrics, network statistics, bandwidth, CPU, all that stuff.
Yep, that makes sense. Yep. Classic example. Yep. Yeah, and I'm sorry, what kind of data did you have? More metric based, yep.
We have a lot of metrics and we have a lot of logs, which are already substantial
Yeah.
data too. And we speak house for it.
Yeah, no, I'm not surprised you do. Yeah.
If you make benchmarks, you speak house too.
Yeah. Well, we should. It's definitely on our radar, especially after this conference. How would you, based on what you've seen, how would you compare ClickHouse versus what we're doing?
We compare ClickHouse
Yeah.
just for graphite. And
Uh-huh.
so we compare it for graphite storage like carbon.
Yep.
Carbon and ISPAR, and we compared it with Cassandra, and it's flashy in this case. And if you have a public benchmark, you can do it and compare.
Great. Sounds good. Anyone else? Time series data? Yes. Which one? This one or the previous one? This one. Yep. So these are, it's inserting rows, and each row has 10 columns. So essentially, I think it's a timestamp in 10 metrics, or maybe I think maybe 7 metrics and 3 tags, right, associated with it. And then the data set is, and we're kind of expanding on the x-axis, but right now we've benchmarked it to about, I think it's like 275 million rows. And we're in the process of the reason why we've only gone this far is because when you're running this on a relational database, it actually takes a long time to run because of the insert rate. It drops and it takes hours and hours and hours. But we're in the process of actually running a further one that goes further out. But we kind of expect the performance to scale linearly, yes.
So at some point, will the graph will be dropped down because that's filled up with memory or something?
Yes. So the question is, at some point does this performance drop off a cliff because of memory? You can only maybe you can install maybe half a terabyte of memory, but maybe that's it on your machine. The way we approach that is that even though this is actually a single node performance, and the current open source database is a single node database, the partitioning we do, the chunking we do, which maybe is earlier in this presentation, it essentially allows us to, we essentially partition your data across your user-defined partitioning key in by time, and we provide the illusion of a single continuous table on top called a hypertable. These chunks, these individual 2D partitions, our design actually allows us to live on multiple machines. So our architecture actually allows for a pretty straightforward kind of scale out. We haven't implemented it yet, but we're planning to in the next several months. And with scale out, right now it looks like the performance will continue to scale out linearly. So we don't expect that cliff. Now the question is, when you get to maybe thousands or maybe 10,000 machines, are there other issues that crop up? We'll find out. But our design allows, for scalability, not just on a single node, but across multiple nodes.
Are these separate Postgres that are running?
Yes, they are. Yeah. So each node is essentially it's a Postgres under the hood, and I don't know how familiar. I know there's a MySQL conference, but Postgres has a notion of an extension. It's actually quite powerful that I don't think MySQL has, that allows you to kind of plug into Postgres and change it completely from the inside. And so what we essentially do is we look like Postgres to the outside world. We support all of Postgres queries. We get the kind of the parse query tree from the parser. We then run our optimizations across all of the nodes, and then we kind of return the results. And so to the outside world, this entire cluster of this entire Timescale cluster looks like a single Postgres database. Your data, even though it's maybe partitioned across, by time vertically, but also by your partitioning key horizontally, that data looks like it resides in one table, even though it's across multiple. Yeah. Any other questions? Okay, well, thank you for coming. Appreciate the questions. I'm going to take one quick picture before you guys go. I don't know. I know it's late in the afternoon, but I don't know. Let's maybe look alive. 3, 2, 1. Thank you. I'm going to stay here afterwards. Feel free to come up. Happy to talk more. Otherwise, enjoy the rest of the day.